Good afternoon to everybody in this webinar on sustainability. I want to explain the very first time. To begin with, I want to say that this webinar will be recorded. So if you do not want to be part of the recording, maybe you should not talk. So this is a webinar on sustainable computing, and let me start by sketching a little bit the context. It is part of a dissemination action of the HiPEAC Vision. My name is Koen De Bosschere. I'm from Ghent University, also the coordinator of HiPEAC. And so HiPEAC has been producing a vision document since 2008, and the last one is from January 2024, number 10. And since 2019, we also have a chapter on sustainability. And this has become more important after the European Green Deal. So in that, the last vision, there are 3 papers dealing with sustainability. First paper is written by myself and Patrick. What does it mean to be sustainable? There is a second paper by Thomas, Lars, and Jean-Pierre on sustainable materials and production. And then the final paper is towards sustainable computer systems and computer architecture by Lieven Eeckhout. So this webinar will focus on these 3 papers, and you can also download these papers from the HiPEAC website. To set the scene a little bit, exactly 6 months ago, this was headline news during the last climate conference that with the current climate pledges, we were heading towards 2.5 to 2.9 Celsius climate heating. And so this is problematic. So some people are talking about the dead end 3C temperature rise. So what does it mean? Well, this is a historical context. So you see here the temperature over the last 24,000 euro. And what you see is in the first 10,000 years, the temperature was growing very fast. And then when the ice was melted, mostly here in Europe, it became more stable. And that was when we started doing, humans started doing agriculture. But here now we see in recent years, so this is the pre-industrial level here, we see that the temperature has risen by more than 1 degree already, and we're already out the maximum temperature that we got in the Holocene. Now we are hoping to stop climate warming at 2 degrees, but some people think that maybe we might end up at 3 degrees of warming, which is way higher than what ever happened in the last 20,000 years. If we do nothing, business as usual, we will end up with almost 4 degrees Celsius increase. What does it mean? Well, if you are in Brussels, this is the current temperature. If we add 3 degrees, we end up with the temperature of Barcelona. And if you are in Barcelona and we add 3 degrees, we end up with the temperature of Agadir in Morocco. But this is the desert, which means that in the Mediterranean, maybe we'll get desertification if the temperature would go up by 3 degrees Celsius. And how is this possible? Well, the reason is, of course, that the carbon emissions keep increasing. So we have been trying to reduce them over the last 20 years. But it leveled out a little bit, but we are still not decreasing. And here you see this is all the carbon emissions that are due to the use of fossil fuels. On top of this is methane. On top of this is nitrous oxide. Then we have fluorinated gases, and this is deforestation, basically, which is also causing emissions. So far, we have not been able to turn the trend down. So what about ICT? And here I'm using the energy consumption, the electricity consumption as a proxy for the emissions, which is at this moment is correct, I think. And here you see that is a report by Schneider Electric from 2021 that they projected by 2030 there will be a dramatic increase in power consumption by the ICT sector. So a part will be due to computing storage. Here you can see the blue one is the mobile networks, and also here the brown one is IoT device use. So these are the main factors that will increase the power consumption. If we would have done nothing in the last few years to reduce the power consumption, so business as usual, it would have been higher. So we did a very good job in trying to reduce the power consumption. But climate scientists expect us to reduce the emissions from 2020 by a factor of 50% by 2030, which means that we have to do more. And that's a little bit of a problem, because many of the things we are doing are not reducing the power consumption, but are increasing the power consumption. For instance, people say, well, maybe the fact that we consume more power isn't maybe not a problem, because there is something called enablement. Our technology will allow other sectors to reduce their emissions. And there is even a report on this. It's called the Smarter Report 2030, but that dates from 2015, so that's almost 10 years old. And there they did the calculation, and say, well, the ICT is emitting in that case 2.27 gigatons CO2 equivalents, but it could save 10 times more in other major industries: agriculture, transportation, heating of houses, and so on. And so that's about 20%. Now, 20% is not enough, because we have to reduce more, like 50%, but 20% is still substantial. And then their conclusion was that for every, that ICT is actually carbon negative, because for every ton of CO2 that we emit, other people will allow to reduce their emissions by tenfold. Of course, this is not true, because they claim that reduction already in agriculture, for instance, so we cannot claim it a second time, otherwise you claim it twice. So the conclusion here is that enablement, as they call it, is not the same as sustainability. There is an effect, of course, but it's not that you can just say, well, we don't have to save energy, or we do not have to save emissions because somebody else is going to do it for us. But this was 21. This was before generative AI. And the people from generative AI say, well, we need lots of energy to run all these models. I see Sam Altman from OpenAI makes a statement here. And if you look at the numbers, it requires lots of energy, but not only lots of energy, but also lots of water to cool the data centers. And it's not a small amount. So Google, for instance, used 20% more water in 2022 than 2021. So that's not just an increase of 1 or 2%, but an increase by 20%. Microsoft, similarly, 34% in just 1 year. And so the hyperscaler, they think, okay, they want to be sustainable too. And so here you see that Amazon has bought a nuclear power plant and a data center next to it, a data center of 960 megawatts. So that's about 1 gigawatt data center. And of course, by doing this, they do not have carbon emissions. But of course, that also means that the local economy, the local society, the people living there cannot use this nuclear power anymore. So then they have to use other renewables, or maybe gas-powered power plants. So this is a really difficult problem. But this is not the only issue. Another issue is that the power consumption of the devices that we are using are not the only source of emissions. Here you see a phone that weighs something like 300 grams, and it has emitted 53 kilograms of CO2 just to produce it. And Apple has done a study, for instance, this for the iPhone 5, and this is the embodied emissions, so the emissions that are caused by the production of the device and the transportation. And the operational emissions are more like 10 kilograms of CO2, which means that the operational emissions we are focusing on so far are only a part, major part maybe, but only a part of the total emissions of the devices, the smartphone, but also the data centers and so on. So here there's a second insight, that power efficiency is really part of the story. And it's definitely not equal to sustainability. It's not because you use less power or only green energy, renewable energy, that you are 100% sustainable. So this is an introduction, and I'm very glad that we have 3 experts here in our webinar. So the first presentation will be by Patrick. What does it mean to be sustainable? And then there will be a second presentation that is more looking at the material side and what happens in the fabs. And finally, there is also a presentation by Lieven Eeckhout on what can we do as computer architects to reduce the impact of the devices we design. So I would like to invite Patrick to share his screen and to start his presentation. In the meantime, I can also tell you at the end of this Q&A, the easiest way to ask a question is to put it in the Q&A box. Then we will look at the questions that we come in and answer them at the end of the webinar. Okay. Patrick, the floor is yours.
Okay, so I'm Patrick Blouet. I'm retired today, but I've been working more than 42 years in the electronic industry and 30 years in the semiconductor industry. And at the end of my career, I did a lot of things around the sustainability for the electronic industry, as I have been the chairman of the Green ECS group, hosted by EPOS. And personally, that I'm looking at all those issues for more than 35 years now. So that's the kind of topic I start to know not too bad. The first point is really to understand about what we are talking about. That when we talk a lot about sustainability. The problem is that when we look at the definition of sustainability, whether it's coming from dictionary or from the finance industry or the lawyers or wherever, or even the European community, there is always a time dimension in sustainability. Something is not just sustainable, it's sustainable for a period of time, which could be clearly defined. It's sustainable for 1 year, 10 years, 1 century, forever. Or it could be sustainable that in order to make sure that our kids will have, let's say, an acceptable future. But in any case, we have to mention the time dimension in sustainability. Without the time dimension, sustainability has absolutely no meaning. We don't know about what we are talking about. And today, unfortunately, very often, we just heard the word sustainability. I reduce my power consumption by 3%, it becomes sustainable. I don't know, maybe yes, maybe no, maybe it's too much, maybe it's far to be enough. So that's we have really to integrate the time dimension in the sustainability. The other point that I would like to set up is that sustainability goes far beyond CO2 emissions. We are talking a lot about the greenhouse gas emission, but we have to make sure that we are not mixing the symptoms and the disease. In these very simple examples, that if you have a pain in your left arm and in your chest, you can take paracetamol to reduce the pain, but there is a good chance that it will not be enough. Because if you make the real diagnosis, that there is a chance that you are starting to do a heart attack, and the treatment will be completely different. So we have really to be very careful about the symptom and the disease. In our case, what we see, we have a lot of symptoms in front of us, like the climate change. We saw the big floods everywhere in the world. Today, greenhouse gas emission, Earth temperature increase, sea level increase, melting of bankies and the ice area in the mountains. But these are just symptoms. And we are in a denial of issue that we say that with electrical vehicle, carbon capture, energy efficiency, all those things, we should solve the issue. The problem that we are in a denial issue, it will not solve the issue. I'm not saying that we shouldn't do it. But we have to understand what is the diagnosis. And the diagnosis we have, it's really that we are really natural resources overconsumption and the massive biodiversity extermination. This is a disease that we are suffering today. And in this case, the treatments are completely different. We have to reduce the resource usage, to reduce the waste, to change our economical model and the societal model, drastic sobriety, and of course that to try to defossilize our world, because today we see that the fossil energy, just from the energy standpoint, but we haven't to forget that fossil matter is everywhere in our life. Without fossil matter, that we are all naked in the street today. So that it's not just the gasoline in our cars. When you look at the ICT domain, the power consumption reduction is not enough to be sustainable. When we look at the trend that today on the ICT, that the CO2 emission have been multiplied by a factor between 9 to 10 in 30 years, more or less. And at the same time, when we look at the semiconductor industry, they did a tremendous work in trying to reduce the power consumption of the elementary transistor. So this means the electronic industry did a very good job, but it's far to be enough that really to contain the increase in terms of CO2 emission for the ICT industry. And one of the reasons is that because we are always changing the use case, and as soon as we have lower power consumption, we have much more use case, and which are in fact generating much more CO2 emission than the gain we are getting from the technology. Just for two points that you see that in 2020, the CO2 emission of the ICT industry was more or less equivalent for the worldwide truck fleet. And there was a trend in which we are before 2030 that the ICT industry should have a CO2 emission equivalent to the worldwide car fleet. So that in this perspective, we see that the electric vehicle that could be part of the solution, but it's far to be the end solution. And we see also that all the new generation of telecommunication techniques are not reducing the power consumption of the ICT industry, even if the different generation reduce for the same amount of information transported. They reduce the CO2 emission, they reduce the power consumption. But once again, the use cases are not constant. So that as soon as we have more bandwidth, we use more video, more data, more everything. So that means that power consumption reduction is far too enough to be sustainable. The other point are the materials that we see that more and more we are using more and more material. We are using more material, higher quantity of one material, but we are using also more and more material that you see on this slide, that on this picture from Intel and IBM, that in 20 years, we use much more materials from the Mendeleev tables for the electronic industry, for the semiconductor industry, and it's still increasing. So that somewhere we are continuously increasing the level of material we are using. And the same for water, that the semiconductor industry and the electronic industry is a huge consumption of water, so that which is a very big issue. And we saw in 2021 with a drought in Taiwan that the impact it had on the population and on the industry. So that's it's a major issue, the materials. The other major issue is the massive extermination of the biodiversity. That's we see that we reduce in average that for the insect and for the mammals, that more or less by 70% the quantity of animals. And this orchestrated by just the human being. That's the first time in the history of the planet that you have a single species which are exterminating at so large scale all the other one. And this cannot continue because somewhere it's a risk for us about our food chain. So it's something we have to take into account. So for me, it's very urgent to rethink the electronic industry. We have to increase the lifetime of our product. Today, in 2022, it was 62 million tons of waste. And the biggest problem is that the CAGR, which is around 4%, so which is quite high. With the recycling is quite low somewhere, that we see that more or less we are not reusing enough. We are not recycling enough. We have to change really our mindset and our way of living that regarding the electronic device. There was something which has been proposed in the ECON project, that European Ecosystem for Green Electronic, which has been proposed in 2022 and which started in 2023. So I know well this project because I have been the initiator of this project when I was chairman of the Green CS group. And we defined the 6R framework. And this framework that there is different pillars. That one is reliability, that what do we do in order by construction having systems which are much more reliable and capable of lasting for a longer time, to reduce the usage of materials, whatever they are, so that changing the manufacturing process, optimizing that the different system or the different package or the different parts we are using. Repairing, that repair is a big thing, that it started in France in 2023. Now it's moving at the European level, but make things that which are repairable. Just remind the mobile phone that we had 10, 15 years ago. It was quite easy to change the battery. Let's try to change by yourself the battery of your mobile phone today. Just a nightmare. So that's why we have to change that. We have to come back to something where repairing become easy, which has a big impact on the complete value chain, because you need to have a spare part which are available. You need to have people trained to do the repairing. You have to be able to repair, to recharacterize, to retest, and so on. So that it's a very big issue. It's not just to say, okay, it has to be repairable. The complete chain, the complete value chain has to be repairable. Reuse, so that's to reuse some some part of the system being a spare part for others. This is important. Refurbish that maybe to divert a system in another application for the one it hasn't been defined initially, but it has reduced performance, but it could be enough for another application. And for, of course, the recycling that to recover the materials. I made a survey inside ST, so I cannot disclose the result, but I made a survey inside ST about the level of recycled material we are using in our manufacturing process, and to be quite honest, it's quite low, and it's more or less the same everywhere in the industry. So that's because sometimes there is two reasons for that. That because people that they prefer to have new materials, or sometimes the materials which are recycled have not exactly the same physical, chemical properties as the initial one, and it has an impact in the process. So this means that we have to think about industrial process which are much more resilient to material with maybe not the best characteristic, but degraded characteristics. So the path to a true sustainability, so we need to have a drastic parametric change in our technology, in our industry. Today we are in a mode where our technology allows me to do something, so I will do it. It's what we see with artificial intelligence, with plenty of things, that it's so easy to do things that we do them. But is it really what we should do? And we have to change to the really mindset where what can I do that is compatible with the environment in which I am living? So maybe put it in first, the constraint of the environment, and to understand in this constraint, what can I do? I'm not saying that we should stop doing electronic, not at all, but we have to do electronic differently. The big point is really the systemic approach, because today, very often, we just look at one parameter and we say that if we improve this parameter, it becomes sustainable. This is completely wrong. We have to really look at the systemic approach and to look at the right metrics that we monitor in order to be sure that to be sure that we integrate plenty of parameters, and without forgetting once again the time dimension, because it's very important. The scalar capability of solution is also very important, because we have to be sure that if we think we have a good solution, it has to be able to scale up, and to be sure that with the systemic approach that is not creating a problem elsewhere which will be bigger than the one we want to solve initially. For instance, that if we want to try to recycle materials that at the end it's creating a huge demand in energy or creating waste that we are not able to recycle, we have to think twice before to go that way. And the thing which is also very, very important, maybe the first thing that we should have in mind, is that sustainability is not limited to technical solution, because there is so big impact everywhere that on the environment, on the biodiversity, all of this has to be taken into account. And we have also to take into account in the sustainable solution the induced change in the economical model and the societal model that it generates. Because, for instance, if we have materials, if we have devices which are lasting longer, but for sure at the end we will sell less device. So that this means the economical model of the companies selling this device will be impacted. We already see that in the textile industry, in the clothes industry, that where the second hand that has been generated decreased by close to 20% of this market. So that we have really to integrate all of this, because without that, we have very poor chance that to have something which will be sustainable. And the last point is, for me, it's obvious, but sometimes it's good to, even if it's obvious, to tell it. The continuous economic growth is not compatible, is not sustainable in a finite world, that we can do whatever we want. At the end, the planet is finished, the resources are finished, and infinite continuous economic growth will not work. So we have to really think differently. It doesn't mean that we have to come back to the Middle Age, but we have to integrate the problem and all the problems we have to face in order to have a chance to find the right solutions. Thank you very much for your time.
Okay, thank you, Patrick, for this nice presentation, just in time. And then we move on to the next speaker, Thomas, who will talk about sustainable materials and production.
Hello, hello everybody. Can you hear me?
Perfectly fine. Yep.
Okay. So I will talk today about, I would say, more sustainable material and production to be in line with Patrick said about the notion of sustainability, which is a relative notion, right? So today I will talk about, well, a bit about the impact of ICT, especially on natural resources. And we will more concentrate on the production of integrated circuit and introduce the concept of fab circularity and lowest production towards some example and then conclude. So our modern time are driven by data. So we are in a data-driven society, and it means that internet users increase much more quicker, and the use in general of data use, I would say, increase much higher than the world population. So we can say that today ICT is about 5% of the world consumption of electricity, and between 2 and 4% of the greenhouse gases. It's much lower compared to building, but still increasing exponentially. So that's why we have to just now to change our practice, especially on the production, because if we can see, if you see this graph in the middle, I would say that 50% of this energy consumption is due to production globally. Another problem is e-waste generation. We produce more and more waste due to ICT. So also we can change the way we consume and design our product to reduce the wastage. So an example about energy consumption, because people usually speaks about Jevons paradox and rebound effect, but this completely depend on the application and the way the ICT is designed at the beginning. For instance, if you compare the electrical consumption of data center, classical, I would say, the data center, and the one that dedicated to cryptocurrency, you can see that energy efficient solution used in data center maintain the global energy consumption worldwide of data center, whereas cryptocurrency are out of control. So it's very important just at the beginning to introduce sustainable, I would say, concept, both at the hardware level, but also at the software level for cryptocurrency, for example. Now, if we consider the material aspects, and we can see that more and more material has been introduced since the 80s in the ICT globally, and now we are up to 60 different material. As Patrick said, well, very few material are recycled within the fab or at the end of life. The ICT equipment recycling is 17%, but this does not include most of the materials. Very few material like gold are recycled at the end. Also, the production of material themselves is concentrated and controlled by a few countries. So this makes a big problems for supply chain. And the conditions of production of the material themselves can be questionable. If you see the news, the recent news about Norway recently that approve deep sea mining. So as you probably know, mining is not a clean industry, and introduce usually some problems, water pollution, etc. But if you introduce mining in the ocean, the pollution, there's a lot of possible pollution that can be also out of control. So, for instance, energy transition will introduce increase of a factor 3 in mining activity in the next years. So we have to reduce in the new technologies the use of materials, rare metals and material. And to do that, we should go toward a more efficient production of integrated circuits. From the energy point of view, manufacturing, so especially for mobile phones, for instance, manufacturing is 75% of the carbon footprint, compared to about 50% for the other devices. And the impact of IC manufacturing increase when the technology node decrease for the most advanced nodes. This is due to an increased number of steps, and also the EUV and advanced lithography, which is a lot, which is energy, consumes a lot of energy intrinsically. So there's many ongoing action now to reduce this energy consumption. So here are some examples. Switch to lower temperature processes, make the process different, so process optimization, reduce heat dissipation, for instance, in or from the oven, and also we can reduce or recycle chemicals, the use of chemicals and water. So this makes a transition to the concept of fab circularity and low waste production in the fab. If I take the example of chemical vapor deposition, which is a very classical way to deposit layers in a microelectronic fab. So you have the materials are in a gas and enter in a reaction chamber, and then you have a chemical reaction on the surface, and then the gas go out. We can say that about 90% of the gas, or between 80 and 99% of the gas that enter as reactants go out as wastes. That means that most of the material goes out of the fab like a waste, and this can be recycled. So if we want to go to a concept of circularity and circular fab, we have to recycle the gases out of these kind of processes. We have also to evaluate all the impact of the manufacturing from of IC, from the raw material to the wastes during all the life cycle analysis. This is made by improved methods that are, for instance, you can find the norms like ISO, and these methods are multi-parametric. So I will give you example after on that. A first example here is a change in the lithography process. So lithography steps are used to define the patterns in our technologies. Here you have the technology nodes, and the smaller the nodes, the more advanced is the nodes, the more mask numbers, so the more step you have, and the more mask number you have, so the more lithography steps you have. And you have different steps here that are described, like the deposit of a photoresist, and then the exposure development, and you define your pattern like this. So photoresist play a role, a central role in our processes, and they are also a source of pollution. And in this research, our colleague demonstrated biosource material for lithography based on chitosan, which is produced from natural resources. And they demonstrated the feasibility of such material. And with this, you can replace I would say, the solvent, which pollutes a lot, with water, for instance. With life cycle analysis, they could evaluate the impact of such processes, and they show that there's a strong reduction, about half reduction on most of the parameter linked to climate change or toxicity or water or use of minerals. There are other action, like using thin layer deposition, pick and place material, use smart cut thin layers to reduce the use of material, recycling, replace, reducing PFAS also, which are a problem for etching or lithography, and some opportunity to make the ICT supply chain more transparent. Introduce life cycle assessment systematically in our industry, use declaration of material on the products, and implement a clear and research ambition plan to explore semiconductor manufacturing. This is examples in the industry with a reference here showing action already ongoing in industry on abatement system, which are the system used to, for instance, recycle some gases, use low global warming potential as alternative on the processes, and many other action that are used today in industry to reduce their impact. More globally, the action should be at different level. So we already talk about the production, like reduce the waste, but also the water used, and recycle water internally in the fab. Reduce the use of critical material, and recycling all the waste. Also at the IC design, there will be a presentation on that, by using new computing paradigms that use less material, and also develops ultra-low power expertise. At the product level, the lifetime should be increase, and that change also the business model. When you want to increase the lifetime at the product level, you have also to rethink your devices themselves, transistor, etc. LCA should be introduced at the design level also. Application also introduce data flow life cycles. That means store less data, because data means also materials to store, and have a sustainable global impact. So I would say globally, we have to integrate circular economy at principle and eco-design at all levels. Thank you for your attention.
Thank you, Thomas. And this brings us immediately to the last speaker, Lieven Eeckhout, who is going to talk about what we as a HiPEAC community can do in order to help the industry by designing more sustainable computer systems. Lieven, the floor is yours.
Thank you for giving me the opportunity. So I work in computer architecture, and the key question that I wanted to answer was like, how can we design more sustainable computer systems? All right. So yes, as my previous colleagues mentioned, greenhouse gas emissions lead to global warming. Sustainability is obviously even more encompassing than global warming. And ICT is responsible for 2 to 4% of the global greenhouse gas emissions. And this is actually on par with the aviation industry, in case you were doubting about the importance of this impact. Now, if you look at the carbon footprint of a computing device, it's really two big parts. There is the embodied footprint for manufacturing, and eventually recycling or dismantling, and we call this respectively the upstream embodied footprint and the downstream embodied footprint. And then we also have operational footprint due to product use during the lifetime of the device. Now, trying to think about how to design more sustainable computer systems, there is a big challenge here because there is inherent data uncertainty. There is massive data uncertainty, actually, regarding the raw material supply chain. There is secrecy in the industry, like yield numbers, for example, will not be publicly released, right? There's unknowns about the expected lifetime of devices. The energy mix at production or at use, intensity of use is really hard to predict for future products, and there's even a rebound effect. And let me try to explain this a little bit more. So an LCA report from Apple from the iPhone 12 actually admits that there is massive data uncertainty. And Apple develops some of their own models, but for the parts that they cannot have reliable numbers on, they are actually using assumptions and industry averages. And when it comes to product use, they only look at the 3 or 4 years of the first users using the device. And then they are using historical data to estimate what is going to be the usage intensity of the devices. Now, I'm sure you've heard about the rebound effect of Jevons paradox. So as Patrick Blouet already mentioned, the use case is not constant. So if you make an individual device more power or energy efficient, that may actually lead to an increase in the use of that device. And this paradox goes back to Jevons, who noticed that when James Watt came up with a more efficient coal-fired steam engine, that the total consumption of coal actually increased. And we also see this in computer systems. For example, in the data center, if you come up with a more power-efficient server, then the immediate reaction from the data center exploiters will be to install more servers within the power budget of the data center. So this is a real effect in computing. So given the massive amount of uncertainty, so how should we deal with this? So how can we still design more sustainable computer systems, even if we have this massive inherent data uncertainty? And my take on it has been to actually embrace it. And this is why I've been working on a very simple model, which I call Focal, a first-order carbon model. It's a top-down parameterized model that is deliberately simple, built on first principles, and the goal is really here to provide insight. And the key idea is to use proxies so that computer architects, computer system engineers can reason about those proxies for the embodied and the operational footprint. And then we can parameterize the relative importance of the embodied versus the operational footprint, while considering different use case scenarios, including rebound effects. And although the model is very simple, it's actually really powerful because if you change some of the parameters and you see what is the impact on the overall conclusions, and if the conclusions are similar across a range of scenarios, you can be quite confident about those conclusions despite there is so much data uncertainty. Yeah. If the conclusions depend on the specific scenarios, then you have to be more careful when reaching such conclusions. So what is a useful proxy for the embodied footprint? As we know, a wafer is a production unit in semiconductor fab. And as you can imagine, then the bigger the size of a chip, the higher its embodied footprint is going to be. If we assume for a minute that we have perfect yield, then we have the normalized carbon footprint shown here on the vertical axis as a function of die size in millimeters square. Then it's almost linear. So even when accounting for lost silicon area around the edges of the wafer, if we assume a Murphy model for yield with realistic numbers from TSMC, then we get a curve like this. So we have a nonlinear effect. But for simplicity, let's use just chip area as a proxy for the embodied footprint of an integrated circuit. And what about the operational footprint? Yeah. So here, I'm making two assumptions, or I'm considering two scenarios. The first scenario is where we consider that the amount of work that needs to be done over a lifetime of a computing device is constant. So if you compare two designs, X and Y, it's really the energy consumption that is a proxy for the total operational footprint of the device, because the amount of work is constant. So here we can use energy consumption as a proxy. Now, as I mentioned before, Jevons paradox, if you have a computer system that is more energy efficient, then it allows for doing, or it incentivizes doing more work. And so here in a fixed time scenario, we're assuming that we're using the device for an equal amount of time. And so if you have a more efficient design, that means that we will do extra work. Yeah. And then as you can see, the total energy consumption of systems X and Y is proportional, or the operational footprint becomes proportional to power consumption. So here under this scenario, we're going to use power consumption as a proxy for the operational footprint. Okay, so now we have a proxies for the embodied footprint, we have a proxy for operational footprint. And so how should we weigh relatively the embodied versus the operational footprint? And that really depends on a different number of factors. There was a very insightful paper from Gupta et al. At HPCA 2021 showing that battery-operated devices like smartphones, tablets, smartwatches, and so forth are much more dominated by the embodied footprint compared to the operational footprint, whereas always-on devices like desktop computers and gaming consoles and so forth are much more dominated by the operational footprint. So the device type really has a big impact. The lifetime, the longer the lifetime, the higher the relative weight of the operational footprint is going to be. Yeah, if we are going to use our electronic devices for longer to reduce electronic waste, this is going to increase the relative contribution of the operational footprint compared to the embodied footprint. The energy mix at production, but also during product use, will have an impact on the relative weight of the embodied footprint versus the operational footprint. So how should we set the proper weight of those two? Well, my solution is to actually parameterize this. So this brings me to this very simple model that shows, that computes in what I call the normalized carbon footprint under these two scenarios, a fixed work and a fixed time scenario. And it consists of two parts. The first part is a weighted embodied footprint proxy. And then the second part is a weighted operational footprint proxy. Okay? And by playing around with these alpha values, we can actually consider different types of scenarios where the embodied footprint is more prominent compared to the operational footprint. We can consider the two scenarios, the fixed work and the fixed time scenario, to explore the effect of design choices on the total carbon footprint of a computing device. And so I've been using this very simple model to sort of revisit a number of archetypal processor design choices. And I've been classifying them in three different categories. Like a design choice is strongly sustainable if it reduces the carbon footprint under both the fixed work and a fixed time scenario. So in a sense, there is no risk for a rebound effect. And a couple microarchitecture and design choices fall under this category. And weakly sustainable means that it reduces the carbon footprint only under a fixed work scenario. So there is a significant risk for a rebound effect under a fixed time scenario. And then some of the design choices could be less sustainable because they increase the carbon footprint under both a fixed work and a fixed time scenario. And there's a couple of examples there too. Yeah. So the examples highlighted in orange here are the ones that I'm going to explain just now. So multi-core, if we use very simple models based on Amdahl's law, and F is the degree of parallelism in the workload, and a BCE is a base core equivalent. It's equivalent to the number of cores. And what we can conclude here is that multi-core is strongly sustainable compared to single core. If we compare, for example, this design point here versus this design point, then the normalized carbon footprint shown on the vertical axis actually decreases. And if parallelism is high, right? If we go from the left curves here to the right curves here, we see even better performance compared to a single core. Parallelizing software is weakly sustainable, and the second conclusion here. So if we increase our degree of parallelism from 50% to 95%, then we have a reduction in carbon footprint under a fixed work scenario, but under a fixed time scenario, the carbon footprint will actually increase. And then parallelizing software is more sustainable than adding cores if you compare these 2 points here. So 32 cores with a parallelism of 90% versus 16 cores with a parallelism of 95%, we can see that we can have a reduction in carbon footprint, both under a fixed work and a fixed time scenario. And in addition, we achieve even better performance. And so parallelising software indirectly can lead to reduced carbon footprint. All right, so multi-core was strongly sustainable. Let's now take a look at a weakly sustainable example, branch prediction, for example. Here, we're comparing a large hybrid branch predictor versus a very simple bimodal predictor. And the key points are that the large predictor achieves a 14% higher performance, leads to a reduction in energy consumption by 7%, and a 6.6 increase in power consumption. So if we have a scenario where the operational footprint is dominating on the right-hand side, then in our fixed work scenario, then the branch predictor is actually beneficial for sustainability. It reduces the carbon footprint. But in a fixed time scenario, it actually leads to an increase in carbon footprint. So we have to be a little careful when using techniques like CPU speculation. And so when the operational emissions are dominating, branch prediction is clearly weakly sustainable. And when the embodied emissions are dominating on the left-hand side, and then branch prediction can even be less sustainable, especially when the branch predicted chip area is more than 2 or 3%, as in this case. And then dark silicon, maybe the big elephant in the room in chip design. So fundamentally, dark silicon trades off chip area for power efficiency. And so that leads to an increase in embodied footprint, and it leads to a reduction in operational footprint. And so the question is, does this lead to an increase or a decrease in overall footprint? And so here I've been using some data from this paper from Eeckhout 2010, showing that accelerators deliver similar performance, but with a major reduction in energy consumption. And if we assume that the accelerators are taking up 2/3 of the total chip area, then when the embodied emissions are dominating, this actually leads to a huge increase in total carbon emissions. And when the operational emissions are dominating, you would need to use the dark silicon chip area for more than 50% of the time, which is obviously impossible because it's dark silicon. So with this knowledge, so can we somehow come up with a paradigm to design more sustainable computer systems? And here I've been assuming a baseline, which is a quad-core processor in the current tech node. And the question then is, how many cores should we foresee in a next generation tech node? And I've been using some data from HiPEAC to make these extrapolations. And on the left-hand side, we have an embodied dominated scenario where alpha equals 0.8. On the right-hand side, operational dominated scenario where alpha equals 0.2. And 4, 5, and 6 cores actually leads to a strongly sustainable design paradigm, because under both the fixed work and the fixed time scenarios, we see a reduction in normalized carbon footprint. Whereas with 7 or 8 cores, we would actually see an increase in carbon footprint under all scenarios, or only under a fixed time scenario when the operational footprint is dominating. So what this really says is that there is a pathway towards more sustainable computer systems. The only thing we need to do is to use the increase in the available transistor count in a more sober way, and not use up all the transistors that are available in a next technology node. And so by doing so, we can actually leverage the reduced carbon footprint per transistor to design more sustainable processors. So sustainability is a grand challenge, and I think this focal model is simple enough for researchers and developers to actually gain quick insight into how to design more sustainable processors. So if you want to know more about this specifically, I can forward you to this AskPlus paper, which I just recently published, and the keynote I gave at HiPEAC earlier this year. Thank you.
Thank you very much, Lieven. Okay, I will invite all the speakers to switch on their camera so that we can do the Q&A session. So as I already mentioned, the easiest way to ask a question is to put your question in the Q&A box or in the chat. That's also fine. I already have one question in the chat, and from Werner. What would be the impact of AI on energy consumption? So with the high necessary computing power, there should be a significant impact. Is anybody here in the room ready to answer that question? I know, Lieven, you have some concerns here.
Yes, for sure. So yes, and there has been some recent reports in the media and the literature about the increase in or the demand for electricity because of AI. And generative AI is everywhere, and it's here to stay. And it's impressive what this technology enables one to do. But the numbers that are coming out of these studies are really concerning in terms of the energy consumption. But what these studies don't even touch upon, for the most part, is the embodied footprint that comes with installing more and more data centers and having more and more GPUs, powerful GPUs in those data centers to actually train the models. And whether training is more important than inference, that's an interesting question. Training the models, you obviously need to do this fewer times than you would need to do inference with the millions and millions of users using these generative AI tools for every and for so many tasks. So yes, for sure, the impact of AI is going to be significant, and I'm sure more research needs to be done in this area to really understand the impact of AI on global warming, for sure.
So I would like to add something. So I was talking in the beginning about enablement, that computing enables other sectors to become more sustainable. I think for generative AI, this is not clear whether there is a form of enablement or not, depending on the application domain for which you are using it. Okay. So I know there is an audience here, so if you have questions, feel free to ask them. Maybe while waiting for a question, I have another question. This is about the life cycle assessments. So I think many people want to become more sustainable in their private lives, also in their professional lives, but sometimes it's difficult to know which choices to make. So even you showed us a model that can help us to make the right choices. But for instance, if somebody would like to buy a car and then he hesitates between an electric car or a carbon-based car, which one is better, depending on how many miles or how many kilometers you drive per year. And so my general question is, how good are they, or how useful are the current life cycle assessment models? And do we more research in this area, or are there already good models around? I don't know, maybe Thomas or Patrick, maybe you are.
Maybe I can begin to answer from the microelectronic production point of view. The problem is, of course, the model and the data that are used to calibrate the models that are used in LCA. And today, I would say we have more and more data, but it's difficult to have all the data and because of course the industry does not communicate very well on this point, and I think there's a lot of improvement, I would say, to have more precise model today, but still a lot of work to do in collaboration with industry to have the good data, especially on the advanced nodes. So I think we there's some improvement, but still a lot to do.
Okay. Well, one case I was wondering is, so based on what Lieven was explaining, so the embodied energy is something, or emissions are something that are very important. And the more intensively you use your device and the longer you use your device, the better it is for sustainability purposes. But if you look at a modern car, an electric car, it's full with electronics. Fortunately, a car will last for more than 3 years, so you will use it for 10 years or longer, which is good for sustainability. But on the other hand, if you only use it for a morning and an evening commute, you might only use it 2 hours per day, and the car is sitting there doing nothing for 22 hours a day. So is there any comment on that?
We have the same problem on mobile phones, for instance. Sorry, Patrick, I try to do it short. Compared to data center, which with intensive, when you have an intensive use, it's okay for planes, for instance. Planes have intensive use, so the cost of manufacturing is lower compared to the cost of the use. So it depends really on the type of product you're talking about, and you have to maximize the use phase. And the use of your products, right? And also the reliability and the lifetime. Sorry, Patrick, you wanted to answer.
Yeah, maybe I can make a remark that I think it's exactly, that's more or less what I explained in my presentation, that we have in all the cases that the sustainability is a multidimensional problem, that we can look at, let's say, at the solution from one angle. If we look at just at the CO2, for instance, we look at the electric car, for instance, it's a very good solution. No problem, almost no problem on that, because it depends on the place where you produce electricity and the level of CO2 in the kilowatt per hour that produced in terms of electricity. But the problem is that it's a multidimensional problem, so you have to integrate the materials, the capacity of the industry that to produce electric cars and so on. And when you integrate all the parameters, that the view you had just with a single one could be completely different. And today, I did personally that survey, I did a report in 2020 comparing, let's say, thermic cars versus electric cars, in integrating the electricity production, the gasoline production, the distribution of the gasoline, and so on. And you see that there is not a single answer. Depending on the country you are, the solution might be completely different. Depending on the size of the car you are using, the solution could be completely different. So we have to understand in this sustainability issue that it's a multidimensional problem, and we have to clearly define what are the boundaries of the system we are studying in order to understand the pertinence or the goodness of the solution. If not, it's very difficult to have a good answer.
Okay,
and on top of that, very often that you see things which are very counterintuitive. That's we have to be very careful about that.
Okay. In the meantime, there is a question by Janos, and maybe Lieven, that's a question you would like to answer. It's about the holistic view, sustainability design. So whether we have to optimize per layer or whether we have to optimize cross layer.
Yeah, that's a very good question. And actually some of the examples that I gave are examples showing that cross layer solution could buy you a lot. If we can parallelize our software, for example, more than it is today, then we can achieve better performance and at the same time reduce carbon emissions, because the amount of parallelism that is available in the hardware needs to be less. Yeah, so the 16-core case could give you better performance and lower carbon footprint compared to 32-core. If you're if you're able to parallelize your software. So that's an example of a cross-layer sustainable design approach. There's for sure there's things that we can do at each layer individually. If you just focus on the software layer, for example, I've been reading a paper that was comparing the overhead of software written in Python versus C or Java. and the amount of energy needed to execute a Python program was several orders of magnitude larger than executing the same functionality in a C program, and it consumes like 4 or 5 times or 10 times more memory. Yeah, so it's clearly that is something that could be done at each layer individually. But again, once you start optimizing in each individual layer, that may create a rebound effect at different layers, and it may create rebound effects in a larger society as things become more efficient. So, and I completely agree with what Patrick and Thomas were saying. I always say, like, making our computer systems more sustainable is a necessary condition, but not a sufficient condition. Yeah, we need to change the societal and economical models as well to actually reduce the total carbon footprint and the total sustainability impact of the computing systems that we design. So it's not a question of doing this or that. I think we need to do everything, and we need to do it holistically.
Okay, thank you. Maybe I have a last question. So the industry and also the European Commission is now actively promoting the cloud edge IoT computing continuum paradigm, I would say. So from sustainability point of view, is this a good solution, or are there better solutions thinkable? Because you need more hardware, I think, over the in different places that you might not use all the time. You need more communication, but on the other hand, you will transmit less data to the cloud or to the data center because you will try to process them locally. So from the life cycle assessments point of view, is there any statement we can make about it?
Maybe just one point about we made some study about IoT devices and how to balance also the edge and the cloud. I think it's Koen, it's a bit of your question, right? And so this is really an application-driven answer, of course, but again, you have to make the good calculation at a good level, and to be sure that each level is used intensively and is not oversized. For instance, your edge device should not be oversized compared to the type of calculation you want to do. So it's an overall optimization, more or less by application. I won't have a general answer because we've seen that depending on the application, the answers are different, right?
Okay, fair enough. Okay.
Maybe, Koen, if I can add something there. Sure. It's really the kind of things where we have to think also with the economic model and the societal model. Because let's imagine that an internet, because we are always thinking about internet that transmitting data and so on, and ending up with a very big data centers that to store data, because somewhere we put something on the server and it's more or less there for forever. Let's imagine another economical model where we keep the same model that for the download, but the people, they pay on demand for the upload, that the more you upload, the more you pay. And you add on top of that, your data are not remnant on internet. When you upload something, is there that for, I don't know, 1 day, 2 days, 1 week. If you want to keep them remnant for 1 month or longer time or forever, in this case, you have to pay. It would change drastically that the way the people they manage their data on internet. Today, you upload a video of a small cat falling down from a chair. It costs nothing. That just upload it and that's it. After that, when you look at the lifetime of the information on internet, is quite short. But nevertheless, we need very huge data center with plenty of data which are just useless. So that just keeping the same infrastructure but changing the business model would have a drastic change on the way that we are using the infrastructure, and as a consequence, the impact it could have on in terms of energy consumption, material needs, and so on.
Okay, good. Thank you very much for all this advice. So I don't see questions anymore, so I propose to close the webinar here. So I would like to add that the recording of this webinar will be put online in the HiPEAC TV, so you can use it in your courses if you want, whatever. Also, the papers that explain all this in fairly good detail, they are online. So if you go to the HiPEAC website, to the Vision, there you can download the individual papers, and you can also use them as reading material in your courses if you want to further spread the word in the young generation. Okay, good. Thank you very much, and see you in the next HiPEAC webinar. Bye.
Okay, thank you, everybody. Bye-bye.
Thank you. Bye-bye.